Introduction. Atomic nuclei study is nuclear physics. There are about 1700 species overall, from deuteron to the uranium isotopes of different kind. Laboratory-made species are there along with the ones in the interior mantle of the stars. Strong interaction is the key here to derive the enormous amount of force having nuclear properties. Electromagnetic interactions of the strong and weak kind also have a role to play here. It is for these reasons the nuclear physics is serving today as a platform where the fundamental properties of the subatomic particles are examined. Studying the fundamental laws of physics becomes easier on this platform. Let us see a brief history on the subject of the nuclear physics first. The role of nuclei in the modern physics is something that is to be learned for anyone. It is such an interesting topic to learn, study and remember forever. Nuclear physics and its history. Since when radioactivity was identified by Becquerel in the year 1896, the concept of nuclear physics is taken into literal consideration as time-tested and valid discussion. Earlier, it was just an assumption without any strong theory to emphasis on the subject matter of issue from any experts in the field of science and technology. It was Becquerel who found the radioactivity for the first time to prove a point, and shed light on the concept of nuclear physics to the outside world. Radioactivity was an unsolved problem all until Becquerel shone the darkened photographic plates while keeping in proximity to certain minerals of the rare earth kind. The inbound curiosity to know more and more about these rare something, Madame and Pierre Curie went on to experiment further and find radium. They were able to successfully separate radium from its ore. Keeping the source on the magnetic field, 3 different activities were noticed. It was then identified as the 3 types of rays. Alpha rays, beta rays and the gamma rays were identified and named later on. Electron, proton and the electromagnetic waves were those in detailed. Only by the time when it was identified and accepted that the central part of atom is composed of nuclei with positive and negative particles as well as the neutron, by Ken Rutherford in 1911, the world nuclear physics studies broadened. Radii of some of the heavy nuclei that were measured by James Chadwick by around 1920 to the order of about 10 inches to 14 meters, it was universally accepted that there is solid and substantial proof with big scope for the future in the studies related to nuclear physics. Meson exchange. It was the Japanese scientist Yukawa who identified finally in the year 1935 that there are meson exchanges that is responsible for the nuclei to be held together with mutual attraction. This force exists between the nucleons. Quantum study began from this point. This is the reason that the nuclear forces are sure to have a finite range. This range is just within the non-zero rest mass that is caused because of the mesons exchanged. Nuclear physics applications. Nuclear physics overlaps with so many other fields of study. Elementary particle physics has a lot in common with the nuclear physics. For example, if you are interested in studying the quark plasma, then you must study a lot in both the field of nuclear physics and the particle physics. That is inevitable. Similarly, if you are entering into the study of astrophysics, then all the relative concepts of stellar evolution or something like the nucleosynthesis are well related to the nuclear physics studies. Nuclear medicine, nuclear energy and the nuclear properties are all interesting topics to study and research for any physics expert. Understanding the force that exists between the nucleons is the prime objective of the nuclear physics studies. How do the nuclei interact with each other is the next level of study. How do the nuclei react with the subatomic matter is the next important study. When you get to know the answers of the 3 questions stated above, you will wonder about the fact that the answers are interrelated to each other as well. Nuclear force. Strongest interaction between the quarks is responsible for nuclear force. Theory for this strong nuclear interaction must be studied to understand the quantum chromodynamics. Low energy extremes are also there where there exists the nuclear force. Therefore, we cannot confine quantum chromodynamics study alone to be a complete understanding about the nuclear forces. A fundamental force that exists between the quarks and the related mystery is not unleashed, and the experiments are aiming at learning this concept at higher energy levels just because of the above-mentioned reason. Foundation of nuclear force can be understood if we can analyze the QCD well. Quantum chromodynamics yet is not a complete way to study the nuclear forces, but still we can do the analogies and chemistry to arrive. That does not guarantee by any means that we can be able to arrive at the structure of the DNA molecules that are starting from the Maxwell's equations. Nuclear structure. Ground states are during when we can find the nuclei. These are the lower energy levels where we can trace nuclei. However, it is possible to inject energies into the nuclei and promote them to the excited levels, as it is in the case of some energized stars out there and in the laboratories. Binding energy. Interesting features are observed when we analyze the binding energy of the stable nuclei. Even the most stable nucleon can be considered for reference. Excited states density. Nucleus can have a number of states as excited. It becomes mandatory to measure this state with different parameters though. Number of nucleons makes up nuclei. Each single nucleon must be occupying a discrete singular particle state. At this state, there are not interactions, or it is assumed to be on the ground state. Individual characteristics are there, especially for these nucleons, but still some special characteristics are also observed in the excited state that is generic. Chapter 1. Structure of Nucleon. All the nuclei in the universe are made up of protons and the neutrons. Nucleons are just the elementary particles. Quarks' degree of freedom illustrates the behavior of these elementary particles. Quarks and leptons are having similar characteristics too. Quarks. What is the fundamental building block of any particle that is part of the universe as a whole? This search is continuously challenging the field of physics experts since all these years. During several phases of the history, the laws keep on improving and our understanding about these fundamental building blocks are varying constantly too, based upon the approved laws that are followed at that juncture. Currently, as per the belief of the worldwide scientists today, matter is fundamentally made upon of leptons and quarks. There are just sole additions to this list, and that could just be the photons and the gluons or the bosons, and a few more. Quarks here can be defined as the fundamental building blocks too. Strong interactions existing between the particles prove a valid point here about the existence of the quarks. Lightest members of the family of hadrons are only taken into consideration in the study of nuclear physics. 6 particles are contained in the nuclei in 3 pairs each. They are named 2. Flavors are the first ones that are followed by the quarks. Then comes in the beauty and the bottom. Then comes in the charms and the strange beauty. Therefore, overall, there are 3 pairs of 6 particles altogether. This is the structure of the nucleon. Quarks are not identified in isolation. You can find it to be in pairs with the antiquarks. Leptons. Bulk mass of the universe is purely made out of the quarks, yet there is room for the next important leptons too. These are lighter particles that are not made out of the quarks. You can identify these leptons in the electromagnetic interactions and the weak interactions of the other kind. Wherever and whenever there is a stronger reaction, you cannot see the leptons there. Chapter 2. Nuclear forces and the dual nucleons interactivity. The interaction between any 2 nucleons can be considered as the central questions in the subject of physics, and its significance is once something that is sure to go very well beyond the nuclei properties. All since 1895, physicists have devoted a great deal of their time and experimentation as well as the mental labour for solving this problem. It could be such that there is no big amount of person-hours that had been given to find an answer to any other scientific question so far in the overall history of humankind. Just recently, we have identified the fact that the nucleons are not the elementary particles, but the overall interactions that are derived quarks force that make them up. This is the time-tested theory that is quantum chromodynamics, which is giving a good description on that structure of hadrons compared to the quarks. Yet it is far less certain about the force of between nucleons, though. Binding energy. Consider deuteron, which is a unique type of nucleus in many respects. You can see the structure to be loosely bound. It has a binding energy which is far less than the average value that exists between the pair of nucleons compared to all the other stable nuclei. Spin and parity. Wave function is better described by parity. Reflection on the coordination system is better represented by using the parity. So parity is obviously considered positive. Spin is the sum of the intrinsic values of the nucleons, which is 0 and 1. Protons and neutrons will have the same wave parity as they both represent the part of the nucleon. Therefore, naturally, the product of the neutron and the proton must also have a positive parity. This is regardless of the nucleon parity as a whole. So naturally, the nucleon of the deuteron is only determined by the relative motion between the two nucleons more than anything else is. Nuclear force and the symmetry. Nucleons interact with each other through two-body interactions. That is, the force between nucleons acts only between a pair of them at a time. The absence of one-body terms in the potential can be seen by contrasting with atomic electrons. In an atom, the electrons are bound to central electrostatic potential provided by the protons in the nuclei. As a result, there is force acting on an electron, even in cases where it is the only one present, such as Il, the hydrogen atom. This is not true for nuclei, as there is no external source to provide a force on the individual nucleon. The only one-body operator in a nuclear Hamiltonian is the kinetic energy arising from the motion of each. Charge independence. We shall assume that nuclear force is charge independent, that is, the only difference in the interaction between a pair of protons and a pair of neutrons is a Coulomb interaction between protons. This is, again, an assumption based on experimental evidence. There is no fundamental reason to rule out a charge symmetry breaking term in the nuclear force itself. As we shall see in the next section, the difference in mass between charged and neutral ions alone implies the possibility of small but significant difference between proton-neutron interaction and the interaction between a pair of protons and a pair of neutrons. Yukawa theory of nuclear interaction. The meson exchange concept introduced by Yukawa was one good starting point for testing the interaction based upon what we can learn through symmetry arguments. To draw a quantitative connection here with the underlying hadron-quark structure, we can relate it to the strength of the meson-nucleon interaction. Phase shifts in the Nucleon scattering. Formula for the nucleon-nucleon interaction potential given was derived only based upon the phenomenon studied using properties identified with the deuteron and symmetries that are noted down in the two-nucleon system. In order to make further crossroads and to infer further studies, the experimental information becomes pivotal. The process of Nucleons scattering for different energies is instrumental in this study. Nucleon scattering, as per the basic, can be studied in 4 different kinds of scattering measurements. Simplest of all is the proton of a proton. This is also called as PP scattering. Accelerating the protons is the first step. The nuclear potential. One pion exchange potential, or the popularly known OPEP, when applied to nuclear forces, tests denote that it could correspond to the experimental data solely for the internucleon distances higher than 2 FM. This is not a surprise, though. Contributions from the sources at the shorter distances can be discrete. Studies are going on today not to mess up with the safety of the labourers who are working in the plants for power production. The study is not adequate, though. In fact, pressure from so many sides and the threat from the other miscreants of the world who are so keen to invest huge amounts of money today to abuse the benefits of the nuclear forces are limitations to spend enough focus on this area today. Otherwise, everyone knows that there is huge potential in this channel for us to rely on the peer demands from everywhere across the world, or to fulfill the needs of aerospace research industry by supplying them with ample power to hack their efforts. With huge potential really revolving around, there are huge threats of the associated kind as well. From one side, there are non-profit organizations from around the world that are pressing the governments not to risk the life of the innocent laborers who are working on these plants. From the other side, there are human activists and agitators who are not willing to take the risks to put the life of the so many innocent people who are living in and around the facilities of the nuclear reactor. Chapter 3. Electron Scattering Form Factor. Electron scattering is so far used to be the suitable tool to study and compare the results of the density distribution of the nuclei. Electrons are point particles. It can be accelerated so easily. Nuclei are what the electron reacts with predominantly. This is happening through electromagnetic interaction. Results are easy to interpret here, as the results can be predicted easily with the previous lab experiments conducted in the similar manner. Remember, scattering is only sensitive enough to charge and allows you to just probe the proton's distribution inside the nucleus. Form factor. This is the method to deduce the density distribution of a nucleus, and it is equal to the square of the wave function. Transfer of momentum. Scattering results can be represented as a momentum transfer function. This is from the electron to the nucleus. Under the limits of non-relativity, we can find triple momentum transfer Q to be equal to K minus KB. The Nucleon form factor. Electron wavelength can become a lot shorter than the typical size of the nucleus at sufficiently higher energies. It is to the order of gigaelectron volts or GeV or even above. To identify the scattering results precisely, charge is distributed within the individual nucleons. Two factors that influence the Nucleon form factor at that instant are the large momentum transfer limits and the proton form. That was deliberately done, aiming at so many political objectives and the real never-say-has-die attitude that was always parted and parcel of this community that were addressed well since the demolitions of the Second World War. Just after the mishap in Japan, there were so many countries across the world that were cautioned and did not even attempt to open any more nuclear reactors again, or even try to shut down their own plants that were running successfully for so many years without any hiccups. Safety is there as such. The top-grade engineering does safety measures and technological experts in the industry to ensure that there are no chances for leakages of the radioactive substances in the air or water by any means under any circumstances. There were measures to keep the unit completely shut and not to allow any leakage to the outside environment. Despite all these installations, it was not completely possible to rely on the modern-day technology alone, not to accept any damage to the dwellers around. This is the major reason. Improvements in the field of nuclear power technologies are delaying since so many decades now. High-energy lepton scattering. What it is all about the electron scattering of nuclei. The wavelength of the electron at lower energies is derived using the Mott formula. When the incident electron energy increases, the nuclear charge distribution size will appear. Nuclear form factors modify the scattering cross-section. The scattered electron, E, and its energy differs from the initial value during the incidence. The difference is the quasi-elastic scattering. When we keep on increasing the energy any further, the wavelength of the electron slowly becomes shorter enough so that we could compare that with the nucleon size. Matter density and charge density. Electron scattering can be used to map the charge density distribution within the nuclei. Measurements are precise, but that gives room for lots of questions. The influence of the neutron on the charges distributed can be studied by using the isotopic shift. Yet, when the charge distribution inside the nucleus is very independent of the neutrons, we are still expecting the isotopic differences to be negligible. This proves that the shifts must be only smaller, and it could be just magnetic moments. In addition, the formed nucleus is not spherical anymore. Magnetic charge distribution shows that it is nuclear magnetism. Combination of two sources originates the magnetism. This is intrinsic magnetic dipole moment. This happens between the nucleons and the protons that orbits around. This is similar to the electric charge density distributed as well. So the magnetic charge density can be obtained as pure divergence of magnetization density, mR. Chapter 4. The alpha particle decay. Nucleon emission can be compared with a particle decay beginning in the lighter nuclei. Plot done for the separating energies can provide a clear picture of nucleon emission or the particle decay, as it is not energetically fired up to the atomic number greater than 150 or so. It could be even for the heaviest of the nuclei, but the lifetimes are longer compared to the strong interaction timing scales. Quantum mechanical tunneling and the bulk properties of nuclei. Alpha particles' energy emitted may tend to be limited to the crucial range of about 5 to 9 MeV. However, the half-lives are sure to vary by several orders counting on the magnitude. This experiment led to the invention of the quantum mechanical tunneling. This is what you can call as a milestone achieved in the field of nuclear physics. Nuclear fission. Alpha decay is not all about it, but in addition to that, the heavy nuclei could also decline in their energy levels through the process of nuclear fission into fragments. It can happen naturally. It can be induced as well. 2 or more fragments can be created in the process of nuclear fission. Inducing the nuclear fission through reactions releases a whole lot of energy. Spontaneous fission reactions are something rare. Induced fission is what that had facilitated much about learning the nuclear fission processes so far in detail. Many nuclei move together ahead of the process of nuclear fission. It is a collective motion. It is possible to visualize the process. It is for the heaviest nucleus that can be energetically easier to assume any shape. Usually, the nucleons are separated into 2 individual groups. It could be overlapping one another. It is only separated by a predetermined distance, which is the difference between the mass centers. Binding energy is not decreased here by any way. Infinite nuclear matter. Infinite nuclear matter could be identified as one idealized system having those bound nucleons all with same density. Electromagnetic and weak interactions are assumed here as just perturbations. This induces transition from one state to other. Rate of these transitions can be examined. That sheds light on the atomic nucleus details. Due to the change in the nucleon and the alpha particle emission, the nucleus state changes. Nuclear fusion. Just like the nuclear fission, nuclear fusion also releases a great deal of energy. Fusion of 2 nuclei can release energy that is called nuclear fusion. Most of the energy in the suns and the stars are just because of the nuclear fusion, or you can say all of the energy in sun in particular is just because of the nuclear fusion of the hydrogen gas. Helium nucleus is what our sun has to produce high-intensity hot gases continuously all throughout the day and night intermittently since millions of years now. Imagine how dangerously this nuclear fusion technique could be used to varied applications by now, then. It is trying to be used in the most organic ways to produce energy. We are running out of the energy reserves in the Middle East. Coal, oil, and the natural gas reserves are depleting today, and under these circumstances, it is good to rely on something materialistic like this technology to use nuclear fusion to produce energy that the world needs. Present and future prospects for nuclear physics. Developments in the field of pure science are often fully or partly controlled by the three-way symbiotic relations that exist between the technology, observation, and the theoretical understanding. We need large accelerators as well as some high-end detectors to study, research, and compare the results to do the analysis. To do the complicated observations, something like the relativistic heavy ion collider is made. There are neutrino observatories. These are expensive to construct. It takes decades at times to bring it to the productive phase. It needs careful planning to go into the design. This is obviously one of the most powerful ways of producing energy. Nuclear reactors are considered to be a threat to the adjacent cities or the town or the villages or even the water bodies and the flora and fauna that is just closer to the production center or the powerhouse just because of these reasons. Yet the amount of energy that you can generate and the potential to get unlimited amount of energy is something that is creating the greed for the governments across the world to do it in one way or the other. The number of nuclear reactors is coming down in numbers all over the world, considering the safety aspects related to the affair. Despite the technological advancements that are consistently coming in every now and then, there are so many types of threats that are increasing in numbers to cause some catastrophic destructions too, under unfortunate circumstances, just like how it happened in the case of Japanese earthquakes recently. Japan was so gifted to have bounced back at such a short notice. Yet, there are so many things that the Japanese government did not reveal to the outside world, particularly about the seriousness of the disaster. Cosmic rays and space observations. Just like the laboratories for varied experiments and research, there are cosmic rays and space observations that are so helpful for the modern-day researchers. A major technological impact is creating in that way when we are ready to do the construction of observatories. When the cosmic rays and space observations are installed in the outside, the Earth atmosphere, then the benefits is awesome. Space stations are serving this purpose already. Otherwise, the combined efforts from the scientists from all over the world must have come up with some stronger solutions of the hour to not to be looking for any alternative sources of energy. This one source, when implemented on massive scales in a safe manner, can be enough to fulfill the requirements of the world energy consumption quite easily. Nuclear force and the ways of utilizing the nuclear forces largely that we know so far is not completely enough for us to get into such novel ideas readily right now. Generic engineering and nuclear physics. There is a strong correlation between the two topics. The affinity of the nucleons and the patterns of study are closely related to the DNA studies. Quantum entanglement is what that is holding the DNA together. If there is no force of binding there, then the DNA molecules unwind. It is hard to imagine the results, though. Nuclear physics of the cell and that of atom are discrete, though. One is to try to find out the ways and means to produce unlimited power and sources of energy using this particular technology. The second menace is that they would take advantage to target the areas of the nuclear reactors to threaten the governments to fulfill their private objectives in case of any claims to be kept, like releasing the terrorists or for any other mean reason whatsoever. Just because of these reasons, the possibilities to use the nuclear physics fully are at stake. It is almost 2 centuries now after the invention of radioactivity, since 1896, but still there is not any significant move forward towards finding so many other types of ways and means to use the nuclear force dramatically for various industrial applications. This is still remaining in to be an uphill task, just because of the simple reason that there are associated threats just like above mentioned. The huge scope in the industry must be made use with the combined efforts made by the governments of the top nations of the world, of the benefits to be reaped for all of the nations of the world. The imbalances in the society can be brought down on a large scale if that is to happen. Either it is deepest nook and corner in the dark continent of Africa or somewhere in the Solomon Islands, power sources will make easier for anyone to live a happy life to the best extent possible when the potential to use the nuclear energy is utilized to a certain extent. Using the nuclear energy to the fullest is not possible, at least for the next 100 years though, as there are so many barriers in the path to sideline which may take at least 10 decades. Moreover, the studies so far are insufficient. After studying well and finding facts in a better way, there are tests and experiments to be conducted on a large scale as well. When everything goes well, then only the high utilization of the nuclear energy is possible to use it in diverse applications from medicine to engineering. Evidence of mutations. Free DNA nucleotides are the reason for the mutations. Chromosomal aberrations are arising in individuals just because of this reason as well. There are people who suffer from so many genetic issues like 21st trilogy or the other genetic problems like additional limbs or the additional fingers or 2 heads in one individual and so on. These are caused by genetic mutations. Chromosomal aberrations of this kind are arising just because of this simple reason that the free DNA nucleotides are contributing to the deviation. Nuclear physics and Dank studies are closely related for so many reasons. However, there is a huge difference in studying the cell and an atom. Nucleus is something physically that is different from that of a cytoplasm. Chemical bonds are formed and broken, but that underlines the life of the cells too. This special issue is studied in detail in molecular biology. There are non-chemical attributes of cell nuclei. Just after the discovery of the electron microscope in the late 1950s, the possibility to study the nucleus under high resolution made certain things clear. Folding of DNA to gigantic lengths, just as it is in the case of DNA of the humans, as organic chains of nucleotides of DNA, were wondrous findings that shed light on the cell against nucleus constituents. Nuclear weapon ordnance. Fission and fusion study to the core is not meant for all, though. Certifications, exposure to this arena of study and research with laurels and accolades to back up will slowly open up the gates for you to get known about the confidential information of the current and the latest kind. When you get to know about the latest findings, it can amaze you. This is one area of study that is being followed keenly with attention by the rest of the world, regardless of whatsoever community you belong. The keenness is just because of the need to be watchful enough not to allow any single dominant community to gain superpower status over the rest of the world to cause big havocs and disasters like what it had happened in the past after the Second World War. The renowned scientists and the researching community are aiming at world peace when they are into such sensitive researches. Even though this lays road to progress to open up many gateways for future prospects, there are militants for the commons to not be aware of the fullest information and the achievements that are latest in the field. Yet when you are a master in this subject, then you are sure to be held with high esteem regardless of wherever you choose to go around the world. It is one interesting area of study as well. Students may be tempted to go and research into some vital concepts which they assume it too easy, but the practical details involved in the affair and life-threatening under most of the circumstances. Tests are conducted in simulated laboratory setups initially to ensure fullest safety and security standards. Bombarding atoms is the basic principle for radioactivity. This forms the base for the universe energy too. Big Bang theory that is universally accepted today and believed to be the real cause for the birth of this universe is purely based upon radioactivity, and there is not big difference from bombarding an atom under laboratory conditions. It is a higher version of this miniature setup. One might wonder about the possibilities of creating new suns, stars and planets if we are mastering in this subject. Yet practically, as human beings, we are not having that much protective measures identified as of now to play with these big things in the material world. Definitely, there is big scope for that in the future though.